So this is the structure of our project, right? And of course, the heaviest work is done inside the lexer, which deals with grammar rules. And these grammar rules are represented by the expression rule, which right now handles plus and minus, binary plus and minus, right? So regardless what happens here, we say that any arithmetic expression that looks like this, right? So let me clean this up a little bit, and just to summarize this a little bit. We say that any arithmetic expression will have the term, it has to have a term part of it, right? So that's why we say, let's call the term rule. And the term itself can be basically the number, right? It can be numeric value, or it can be something that has plus or minus in front of it, right? Or it can be a sub-expression inside parentheses, right? So that's the way it's going to be evaluated. And then we say that we will assume that this is left-hand side in case if there is a plus over here. So if we say 1 plus 2, right? So a valid expression could be just 1 or 2 or 3. That would have only one term, and this can be immediately interpreted as the result of the expression. But if we have more of that, 1 plus 2 plus 3 and so forth, if we have more elements of that expression, then basically we say, in that case, if that's the case, we will consider the first number to be just the left-hand side, and we will move on to the, continue with this expression, and we'll say if there is a plus or minus that follows, then we basically create a fork node, right? So just a reminder that we said that, let me just basically clean this up one more time for you, right? So in the first situation is that, say we detected 1 in the input. So the node 1 is produced, right? And it has numeric value. Then we detect that there is also a plus. We create a node called fork, right? Fork over here, and we give it a left-hand side, and then we will evaluate the right-hand side as, another part of this expression. So eventually it's going to be organized like this. In case if there is also another part over here, say plus 3, then again a fork is created, because this is done in a loop, right? So a fork will be created with another plus, and this time this entire result of the prior part will be given to this plus as the left-hand side, and again it will continue with this, with the rest of this expression, and will add another node on this side. So that's how this is constructed. If there's another, say, multiply by 5, right? There's more work to do. Then what's going to happen with all of this is that, of course, in our grammar, what we do is that the multiplication has higher precedence than this addition, right? So what it means is that this needs to be evaluated as one sub-expression. For that reason, multiplication is actually implemented as part of the term, which is down here, a sub-rule that we use, right? So we say then it's very similar organization. The term grammar rule says that it is either the primary on the left-hand side, or it can be any number which is implemented by this loop, any number of multiplications and divisions. So both multiplication and division have the same precedence in terms of the operation. So therefore, what's going to happen is that this time, this will not take place. Instead, the term first will create node such as 3, right? It will be able to process this as a primary inside the term rule. Then it will detect that there is a multiplication, right? So it's going to create the fork with multiplication and give it the left-hand side like this. Then it's going to continue on with the left-hand side primary and collect 5 and place it right here. And then the term will return this entire sub-expression. And when it happens, right, this entire sub-expression will be attached to the rest of the expression. So that's why multiplication will be handled as a single unit. Let's actually demonstrate something like this when we run our program. So this is 1 plus 2 plus 3 times 5, right? So let's take a look at what it does at runtime. So we're going to say 1 plus 2 plus 3 times 5, right? So right now, as you know, I am not doing the computation, but if you compare what I have in this demonstration right here, right, to what I get in my computation, you can see that this plus right here, right, so this specific plus operator right here is right at the top. It's this guy right here. Okay, so then we have another plus, and apparently the way I print the internal tree like this, the tree of these nodes, right? What happens here is that this plus is representing the left-hand side, this plus, right? And naturally, this plus has 1 and 2, the two left-hand side and right-hand side. Then we have multiplication, which represents this node. And this is clearly actually the right-hand side of this top-level plus, right? So this top-level plus over here has the left-hand side, which has the multiplication node, and multiplication node naturally has 3 and 5. The only difference is that this part of the tree, right? This part of the tree was constructed by the term rule, right? So that was done by a separate grammar rule, and that's the outcome of it. Okay. So that's what we have, and luckily you don't have to do anything to implement this. It's already implemented. All the grammar rules are implemented. So we can switch over and discuss what is our challenge in terms of finishing this homework. Let me save the segment and we will move on.